Hello, everyone. Welcome to this video recording of one of our topics in Math 101. Now, I was looking at the remaining topics for the course. We still have to finish talking about orders or ordering relations on a set. Second, we still have to construct the set of natural numbers, which will lead into the third remaining main topic in the course, which is the cardinality of sets, where we'll talk about cardinal numbers and different levels of infinities. All right. So medyo kulang na tayo sa oras. That's why I was forced to do these video lectures and assign them as watching assignments for you guys. So for this week, I will talk about three things, and I decided to split it up into two or three video lectures para mas madali nyo siyang mapanood. I mean, you can insert one video during a lull time during the weekend or before you sleep at night. So may tatlong bagay tayong i-discuss in this series of lectures for this weekend. We'll have the well-ordering principle, which we will do in this video, and then we'll talk about Zorn's lemma in the next and the axiom of choice next time. And then it's in preparation for the upcoming week, starting December 14 until December 17th, where we will talk about piano's axioms and see if we can also start talking about the cardinal numbers. All right. So let's get going. We'll talk about the well-ordering principle, but before we begin, let's recall what some of the things that we already learned from the previous discussions. We talk about partial orders, and we said that the partial order on a set, say capital A, is simply a relation on A satisfying three properties. First, reflexivity, then anti-symmetry, and then third is transitivity. And then we talk about some ways of representing partial orders via lattice or lattice diagrams or poset diagrams. All right. Tapos sabi natin, on a set A, there could be several partial orders that can be defined as long as such a relation satisfies all three properties that we have enumerated before, right? And if you want to talk about a very specific partial order on a particular set, then we can call it as a poset. When we write a poset, right, we usually write it in this way. So we have the set A, and then the relation, the specific relation that we want to consider, right? So pag nakakita kayo ng gantong notation, ibig sabihin si set A, together the relation precedes, is a partial order. So tinatawag natin tong poset. All right? And then we said that in a partial order, two elements are comparable if we know that one precedes the other or vice versa. Right? So kung meron kang dalawang elements, alam mo kung sino yung nauuna sa kanila dun sa partial order, then we say they are comparable. Otherwise, they are incomparable. If neither precedes the other, then they are incomparable. All right. And then we look at another specific type of partial order we call a total order, which is a partial order where any two elements are comparable. Okay? So yun yung mga natutunan natin before. But so that gave us our discussions before gave us the tool to check whether a given relation on a set A is a partial order or not. Okay? But aside from that, a bigger question or the next natural question to ask is, pag binigyan ba ako ng isang set, pwede ba ako makahanap ng partial order dun sa set na yon? So if we are given an arbitrary set, can we construct a partial order on that set? Kasi nga, in almost all of mathematics, ordering is a very important thing. And you will learn that in your future major courses where you will try to establish an order, say, between sets, between functions, etc. All right? Now, the answer to that question is in the affirmative, and we will use the well-ordering principle in or to illustrate that topic or to answer that question of whether or not we can define a partial order on any set A. All right. So that's the goal of this particular video recording, which will start with definition one, where we talk about a first or least element and the last or the greatest element, right? So first we will assume that we have a set A together with a partial order on it, be it a partial order or a total order. So the element Z in capital A is called a first or least element if or if Z precedes all elements of the set. Ibig sabihin, kung ililista mo in a partial order, si Z dapat lagi siyang mas maliit. Sort of. When we say mas maliit, siya yung nauuna dun sa partial order when Z precedes all elements of the set. So dapat comparable siya sa lahat ng elements ng set, tapos siya lagi yung nauuna. It precedes all other elements of the set. Okay. In contrast is what we call the last or the greatest element. An element W of A is the last or the greatest element in a set if it dominates all element X of capital A. Kung ililista natin lahat ng elements ni A following the partial or the total order given, yung element W siya yung nasa dulo. Siya yung comparable siya sa lahat ng elements ng set, tapos siya yung nagdo-dominate sa lahat ng elements ng set natin. Alright? Now, it is easy to imagine that if the first and the element exists, then they would be unique. Isa lamang yung makukuha nating first element, isa lamang yung makukuha nating last element kung sila ay nag-exist. Alright? And that's the big caveat here. Hindi lagi nag-exist ang first at saka last element. Alright? Let's take a quick look at an example here para lang ma-visualize natin ano yung ibig sabihin ng first at saka last element. Nakita natin yung technical definition, which would be your go-to tool when you try to prove things about the first and the last element. All right? Pero ito, i-visualize natin. So in example 3, we consider the set A consisting of the letters X, Y, Z, W, and T, and we assume that it is ordered according to the lattice diagram shown in the figure. All right? So remember, it's a lattice diagram. The higher it is in the diagram, meaning it dominates everything that is below it, right? For instance, Z precedes Y, or in other words, Y dominates Z, all right? And then X dominates Y, and by the transitivity of the partial order, X dominates Z. All right? Ganun yung pagdrawing ng poset diagram, right? On the other hand, since there is no line connecting Y and W, and there is no there's no bottom down route that can lead us from Y to W, then we say Y and W are not comparable because neither Y precedes W nor W precedes Y. Okay, so yan yung ibig sabihin ng poset diagram. Now, can you take a moment to see ano yung first at saka last element nung partial order natin illustrated with a poset diagram if they exist? So you can pause this video right now, tally your answer, write down your answer, and then after 2 seconds, I'm gonna reveal the answer. All right? So pause now. All right, so hopefully nasulat nyo na yung sagot nyo. So let's see if our answers are correct. The first question, do we have a first element? And if we do, sino siya? All right? The answer is wala tayong first element. Kasi remember, ang usapan, para maging first element, dapat pini-precede niya lahat ng element dun sa partial order o dun sa poset natin. All right? Now, the candidate to become the first element will be those at the bottom end of the lattice diagram. And if we look at this, all right, we have two candidates, Z and T. Now again, for it to be the first element, it should precede all elements of our poset, all right? Now Z precedes Y, and Z precedes X by transitivity, all right? However, Z doesn't precede W, nor Z precedes T. At dahil doon, si Z, hindi siya pwedeng maging first element kasi hindi niya piniproceed si W, hindi niya piniproceed si T. Ang requirement ng definition to become the first element is that this will precede all other elements of the poset, right? So that means Z will not be the first element, right? In the same token, T cannot be the first element because it is not comparable to Z, meaning it doesn't precede Z. It doesn't precede Y either, so automatic, hindi na siya pwedeng maging first element. So this particular posit is a nice example to show us that the first element need not exist in a poset, right? On the other hand, we have a last element. Remember, the last element or the greatest element must dominate all other elements. So if you're looking for the last element, you better look at the top end of the lattice diagram. And if we do so, makita natin si X sitting on top of the diagram. All right? In this particular case, we can say that X dominates Y kasi nasa ilalim niya si Y connected with a line. And then X also dominates Z, all right? Because Y dominates Z, X dominates Y. By transitivity, X will dominate Z. So there is a top-bottom route going from X to Z. And in the same token, X dominates W, W dominates T. So by transitivity, X also dominates T. So thereby making T a dominant element against all other elements in the set A. So we say X is the greatest element. And I can use the article the kasi nga nag-iisa siya. By remark 2, we know that when the first and last element exist, they will be unique. So wala nang ibang last element or greatest element aside from X. All right? So I hope that trashes out the definition. All right? So perhaps let's look at some other poset diagrams here. So we have seen this before. This is from example 13 from chapter 4.1. So I guess this is the inclusion diagram or the diagram for the inclusion partial order on the set containing the letters little a, little b, and little c. All right. Now, can you guys pause for a moment and think, is there a first and last element for this poset? And if yes, what are they? So you can pause it now, then I'll reveal the answer momentarily. Okay, so I hope you got your answers written down. Now, the first element here is the empty set, because the empty set rests at the bottom of the lattice diagram, and surely we know that the empty set will precede all other elements in the power set of capital A. Kasi we know that the empty set is a subset of any other set. So dahil subset yung partial order natin dito, we are sure that the empty set will be the first element. On the other hand, the greatest element or the last element is the set capital A itself, because it is the superset of any other set in the power set. All right? So kasi siya yung pinakamataas, dinodominate niya lahat ng elements ng power set because any element of the power set is a subset of capital A. Right? So, nagagamit ko yung properties ng pagiging subset kasi ang poset natin dito ay yung power set ni A together with the inclusion relation. Okay? All right, so I hope that's good. Let's see. All right, here are some more examples. And this will show that not all ordered sets have a first or last element. Katulad nung nakita na natin dun sa unang example. Now, for instance, let's consider number 1. The set of all x's such that x is strictly between 0 and 1 together with the natural order. Pag sinabi nating natural order for the set of real numbers, siya yung less than or equal to relation. All right? Now, we say na siguro inisip nyo, okay, kailangan, para magkaroon ka ng first at saka second element, dapat yung mga candidates para maging first or last element, they must be comparable to all other elements of the set A, right? Kasi nga dapat siya yung nagpe-precede or nagdo-dominate sa lahat ng elements ng partial order. So dapat comparable siya sa lahat. So siguro magkakaroon pala tayo, at the back of your minds are thinking right now na siguro magkakaroon tayo lagi ng first at last element kapag ka meron tayong total order. Pero this example, the first example, will show that even if we have a total order, it is not guaranteed to have a first or last element. All right? So, balikan natin. Set A is the set of all numbers that are strictly between 0 and 1, together with the natural order. Now, totally ordered yan. Kasi pag binigyan ko kayo ng kahit anong number sa pagitan ni 0 at ni 1, kahit anong pair of numbers, we will know for certain which one is less than or equal to the another. So it's a total order. Pero wala siyang first or last element. Can you think of why wala siyang first or last element? Right? The answer here is there is a nice property of real numbers. Sa real numbers kasi meron siyang density property. Sa pagitan ng dalawang real number, meron pang isang real number. All right? So if we will draw this set, all right? Parang ganito yan. 0 dito, 1 dito. Ito yung poset diagram niya. Dinrawing ko lang siya horizontally, pero you can draw it vertically as well. Now, kapag ka meron ka ditong number, say A, meron ka number ditong B, dahil si A ay nasa kaliwa ni B, we can say that A is less than or equal to B, or A precedes B. Now, to see what could be the first element, then we will be looking at the left end of our lattice diagram. So, zoom in tayo dun sa kaliwa. So, pwedeng sabihin nyo, okay, baka naman si 1 over 100, siya yung least element. Because definitely, there would be a lot of numbers that are greater than or equal to 1 over 100. So, maganda siyang candidate para maging first element. However, by the density property of real numbers, sabi ng density property na yun, sa pagitan ng dalawang real numbers, katulad ni 0 at saka ni 1 over 100, meron pang isang real number. So there is at least one other real number here, say yung midpoint ni 1 over 100. So that's gonna be what? 1 over 200? All right? Nandun pa siya sa kabila. And 1 over 200 will precede 1 over 100 in the natural order. So X na yung 1 over 100, hindi na siya yung least element. Right? Kasi nakakita na tayo ng number na mas maliit sa kanya. However, again, I will appeal to the same property, the density property. Sa pagitan ni 0 at saka ni 1 over 200, meron pang isang real number. Meron pa diyang 1 over, halimbawa, 1 over 1 million. And definitely 1 over 1 million is less than or equal to 1 over 200. So 1 over 200 cannot be the first element of the set A to get in this natural ordering kasi nga mas maliit sa kanya si 1 over 1 million. But again, density property will kick in. Between 0 and 1 over 1 million, there will still be a natural, a real number. So ibig sabihin, hindi pala to ang magiging least element. And the process will go on in a never-ending fashion. So ibig sabihin, laging may mas maliit pa dun sa candidate ko para maging first element. Now, that is enough to say that there is no first element in this set, right? The same thing goes for the greatest element. This set also doesn't have a greatest element because again, if you have a candidate here for the greatest element, you can always find a number between that candidate and 1 that will be your new candidate. Pero yung bagong candidate na yun, matatalo pag in-apply mo uli yung density property. All right? Now, it would be a very different story if we will include 0 and 1 in our set A. Kung kasama si 0 at saka si 1, then definitely the least element would be 0 kasi wala nang mas liliit pa na element ni capital A kaysa kay 0 at wala pang wala nang mas lalaki pa kay number 1, right? Yun ay kung ang set A ko ay set of all x's that are that are greater than or equal to 0 but less than or equal to 1. Saka ka magkakaroon ng first at saka second element. So yeah, it is a little tricky. Not all total orders will have a first or second, a first or greatest element. All right. So posibleng wala pa rin sila. Now, second example here is in this poset, the set of natural numbers together with the natural order less than or equal to I think I need to make a correction here para maging consistent tayo. The set of natural numbers starts at 0. Ito yung sinabi na natin when we talk about PMI. And that will also be our convention when we talk about Piano's axiom next week, right? So 0 is the first element with the natural order. It's a total order, right? Less than or equal to is a total order in n. So there is a first element, si 0. Pero walang last element. Kasi pwede mo sabihin, okay, ang candidate ko para maging last element ay si 1 million. Pero 1,000,001 is another natural number which is greater than 1 million. So 1,000,001 would be my new candidate for the greatest element. But then again, there would be 1,100,000 which dominates 1,000,001. Ibig sabihin, lagi akong may nahanap na mas malaking natural number kaysa sa isang natural number. Therefore, even though we have a total order here, this will not have a last element, right? And then number 3, I guess this is this can be extrapolated from our previous example before. If we consider the poset of the power set of any non-empty set A together with the inclusion relation, the null set is always the first element because again, the null set is a subset of every member of the power set of A, and the last element is the set A itself because every member of the power set of A is a subset of capital A. Okay, so in summary, we can say we can accept remark number 5. Not all ordered sets, even if it is totally ordered, have a first or last element. All right. Now, kung wala, bigyan natin ng magandang pangalan yung mga partial orders, yung mga posets na laging may first element. At tatawagin natin sila yung mga well-ordered set. Okay? And that's in definition 7. A poset, A together with a relation with a partial order less than or equal to, is called a well-ordered set if and only if each non-empty subset of A has a first element. So dito pala, pag nakakita kayo ng ganito yung pagkakasulat ng poset, it doesn't mean that this less than or equal to is the natural order that we define. Because for one, walang sinabi dun sa definition. So kapag ka hindi strictly sinabi or hindi explicitly sinabi dun sa problem or dun sa statement na yung less than or equal to ay yung natural order o yung less than or equal to na relation, then you cannot assume it to be so. It could be treated as a random symbol or a placeholder sign for an arbitrary partial order, right? So kung ang meron tayong partial order, tapos kinuha natin yung kahit anong non-empty subset ni A, tas laging may first element, yung non-empty subset na yon, then we will have a well-ordered set. So medyo mas restrictive to kaysa dun sa pagiging isang partial order or total order. Yung mga partial orders at mga total orders, hindi necessarily meron silang first element. Kung may first element sila, and then okay. But having simply a first element doesn't guarantee being well-ordered. Kasi ang kailangan natin para maging well-ordered, dapat lahat ng non-empty subset ni A ay may first element with respect to the given partial order. All right? Now, let's look at some quick examples. The partial ordered set n together with the natural order less than or equal to is a well-ordered set. Kasi kahit anong non-empty subset of n has a first element. So di ba ang n nagsimula kay 0, 1, 2, 3, 4, 5, 6, 7. It's a total order. So pwede nyo tingnan itong listahan ko na to as the poset diagram. Kasi pag nasa kaliwa siya, ibig sabihin it will precede anything on the right. Kasi natural order lang naman yan. So pag kumuha ko ng kahit anong subset ni n, guaranteed na may makukuha akong least element. Right? So that means this is a well-ordered set. Right? This guy and together with the natural order is well ordered. On the other hand, kung balikan natin yung isang example natin, yung set A natin, which is the closed interval 0 to 1. Again, this would be the set of all x's such that x is greater than or equal to 0, but is less than or equal to 1, right? We know that this is a total order. A together with the natural order less than or equal to is a total order, all right? And we have concluded that 0 is the first element of this poset. But having a first element doesn't guarantee being well ordered. Kasi dapat lahat ng subsets ni A dapat magkakaroon ng first element. Dapat lahat. So I can just take as an example the ordered pair 0, 1. Sorry, not the ordered pair, but the open set or the open interval 0 to 1, right? And this is clearly a subset of A. Tinanggal ko lang si 0 at saka si 1. But we have seen in one of the illustrations before that the open interval 0, 1 doesn't have a first element. Kasi ang tanging candidate natin dito para maging first element ay si 0. Pero si 0 ay wala dun sa open interval. So that means this is a subset of A that doesn't have a first element. So the closed interval 0 to 1 together with the natural order is not well ordered. Okay. Now another example is another totally ordered set is the set of integers together with the natural order. It is a total order, and yet it is not well ordered. Kasi si Z itself, wala siyang first element. Kasi sa natural ordering, kung ilista mo yung mga integers, you will have negative large integers up to 0, and then 1, 2, 3, until the larger integers. So wala kang makikitang first element sa set Z, and much more with any of its subsets or most of its subsets. All right? So dahil walang first element, lahat ng or merong mga subsets si Z na walang first element with respect to the natural order, then we say that Z is not well ordered. Okay? Now, come to think of it, exercise 10, is this poset, power set of an arbitrary set A together with the inclusion relation well ordered? Why or why not? You can pause now because I will reveal the answer momentarily. Okay, so I hope you got your answers written down. Let's see. To illustrate, the answer here is no. Hindi well-ordered power set together with the inclusion relation, right? To illustrate this, let me go back to this previous example that we have, all right? It is not a total order. It is a partial order, pero okay lang yon kasi ang usapan para maging partial order, para maging well-order, para maging well-order, dapat ay lahat ng subsets niya ay may first element. Okay? So the idea here is, if we consider, say, a little set capital A consisting of 3 elements A, B, and C, all right, meron siyang first element, the empty set. Pero pag kumuha ko ng subset, all right, pag kumuha ko ng subset ng power set, kumuha lang ako ng ilang mga sets mula dito, pwede kong kunin si set A, si set containing AC, tapos si set containing A, tapos si set containing AB. All right? Now, if I will draw the sub-poset diagram for this set, or actually, ayoko pala si... Okay, sige, simulan natin dito. Right, so, yung poset diagram, ganito yung magiging itsura niya. Right? So, the subset of the power set consisting of these 4 members will have a first element, set containing A. Because set containing A will precede any other element in this truncation of the poset diagram. All right. However, kapag ka pinali set BC lamang, all right, now the set containing A will not serve as the first element anymore in this subset of the poset diagram. Bakit? Kasi si set containing A doesn't precede the set containing BC because the set containing A is not a subset of the set containing BC. So, pag kumuha ko ng apat na elements ng power set, tapos dinrawing ko yung poset diagram, makikita ko na yung restriction ng partial order ay walang first element. This guy will not serve as the first element. Kasi nga, hindi naman siya comparable dito. Right? So that means we have found a subset of the power set of A that will not have a first element. So that means the poset consisting of the power set of A and set inclusion is not well ordered. Okay. Now, let's look at some nice results. Proposition 11. In Proposition 11, we say that every well-ordered set is totally ordered. And it's a nice property, right? Alam na natin na hindi lahat ng total orders ay well-ordered. Pero the converse pala is true by Proposition 11. It tells us that every well-ordered set is totally ordered. And let's try to write a proof for that. Okay. So again, we want to show that a well-ordered set, say A, together with the precedes relation, is totally ordered. Yan yung gusto nating ipakita. And recall, what does it mean to be well-ordered? Ibig sabihin, lahat ng subset ni A ay may first element. All right? At ano yung kailangan para maging totally ordered? A set is totally ordered if the partial or if every element or every pair of elements in the set are comparable. Pag kumuha ko ng dalawang elements ni capital A, dapat silang dalawa ay comparable. Ibig sabihin, one precedes the other or vice versa. All right. Now that's what we want to show. So what I'm going to do is in the proof, I will consider two elements of capital A, say X and Y. All right. And I want to show that X and Y are comparable, meaning either X precedes Y or Y precedes X. Right. But I will use the property or I will use the assumption that this partial order is well ordered. All right. And take note of the fact that the set containing XY is a subset of A. Thus, the set X comma Y has a first element. Kasi nga, well-ordered siya by assumption, right? Sabi ng pagiging well-ordered, kahit anong subset niya, specifically the subset containing X comma Y will have a first element. Tapos, dalawa lang naman yung candidate para maging first element. Either si X yung first element o si Y yung first element. So thus, we can say that either X precedes Y or Y precedes X, right? So in either case, we know that in either case, we know which element precedes which. In other words, X and Y are comparable. Because our choice of X and Y are arbitrary, so kahit ano palang dalawang elements ni capital A ay comparable dun sa well order. So this means that the set A, together with the relation, is totally ordered. And that ends our proof. All right? And this is a nice thing kasi yun pala, kapag ka meron kang well-ordered set, napakaganda ng property na yon kasi kung well-ordered siya, automatically siya ay totally ordered. Okay? Now, it would be nice if you can try exercise 12 that is asking you to prove that every subset of a well-ordered set is well-ordered. And I think you will just play on transitivity of being a subset. Right? So try it out and then send me an email or a chat in MS Teams if you had any problem with exercise 12. And then the entree for today's discussion, actually hindi na nga entree, parang pa-dessert na to kasi ito na yung last, the well-ordering principle. The well-ordering principle says that if A is a non-empty set, then there exists a total ordering of A such that this guy is well-ordered. In other words, every non-empty set can be well-ordered. Remember in my introduction earlier, I posed the question na pag binigyan ba ako ng isang arbitrary set A, can I construct a partial order on it? Well, the well-ordering principle says yes, and actually you can do more. If you're given any non-empty set, then you can have a well-order. Okay? Hindi lang partial order yung makukuha mo. Hindi lang total order yung makukuha mo. Makukuha mo ay isang well-ordering. Why I say mas maganda yung pagiging well-order? Kasi nga partial order siya na lahat ng subsets ay may first element. Tapos yung pag well-ordered siya, automatic na nagfa-follow na isa siyang total order. Alright? Now, actually, it's not just telling us that you can find a well-ordering of the set. Yung statement dito, ang sinabi niya ay makakukuha ka ng isang total order. Tapos yung total order na yon ay isang well-order. Right? So, ang sinasabi nito ay merong isang order o isang relation kang ma-define sa isang set kung saan yung order na yon ay isang well-order. Right? So, hindi ibig sabihin na halimbawa, set of integers. Sinabi na natin kanina na, okay, the set of integers together with the natural order is a total order, but it is not a well-order. Well, the well-ordering principle promises us na dahil si Z ay non-empty set, then makakapag-define ako sa kanya ng isang total order na well-ordered din. And of course, that promised relation by the well-ordering principle will be different from the natural order kasi alam na natin na yung natural order, though it is a total order, hindi siya well-order. Alright? So kailangan ka mag-define. Ang sinasabi lang ng well-ordering principle, kaya mong mag-define. So any search for such a well-order is not in vain kasi ginaguarantee ng Theorem 13 o ng well-ordering principle na lagi kang makakahanap o posible kang makahanap ng isang well-order sa isang non-empty set. So kailangan lang nating maging clever sa pag-define ng relation na yon. Right? So in illustration 14, we show how the well-ordering principle or papakita niya kung ano yung mga posibleng well-orders na pinapromise ng well-ordering principle. Yun nga lang yung konting, napaka-powerful, don't get me wrong, napaka-powerful ng well-ordering principle, pero hindi niya sinasabi paano mag-construct. Sinabi niya lang, kaya mong mag-construct, lagi kang may mahanap, pero hindi tayo tinuruan ng well-ordering principle kung paano hanapin or paano i-construct yung well-order na yon. Okay? But usually in math, proof or statements of existence are powerful enough. Tapos bahala na tayo mag-develop ng ways on how to find it. All right? And that's what was done in example 14. So let's consider the set of all integers. And we have noted already that the less than or equal to relation is a total ordering of Z, but it is not well ordered kasi may mga subsets si Z na walang first element with respect to the less than or equal to relation. But thanks to the well-ordering principle, we know that there could be a well-ordering of the set Z. For instance, itong unang bullet, isa siyang total order. So ng set Z, imagine nyo lang to as a poset diagram or a lattice diagram wherein pag nandun ka sa kaliwa, ibig sabihin piniproceed mo yung nasa kanan. So in this relation, 0 precedes 1, or 1 dominates 0, 0 precedes negative 2, 0 precedes negative n, negative 2 precedes negative 3, negative 2 precedes 3, and so on. So yan yung itsura ng ordering. Total order siya kasi mag-isip ka ng dalawang integers, makikita mo kung sino yung nagpe-precede kanino. Alright? By the way, siguro explain ko yung process dito. Nagsimula siya kay 0, tapos sumunod siya kay 1, tapos in-insert niya si negative 1. Tapos nilagay niya si 2, in-insert niya si negative 2. Tapos si 3, in-insert niya si negative 3. So sa ordering na to, si negative 3 dominates positive 3. Alright? But in this way, we have created a well order for Z. That is, of course, we know that any well order is also a total order. All right? So because pumili ka ng kahit anong subset ni Z, lagi tayong may mahanap na first element kung ito yung ordering na i-consider natin. So you can pick, say, the subset containing all negative integers. The set of all negative integers, together with the relation in the first bullet, will have a first element, and that is namely -1. But it will not have a last element or greatest element kasi nga, and so on pa yan. If you take the set of all positive integers, then the first element will be 1. Kasi 1 precedes 2, which precedes 3, which precedes 4, which precedes 5, and so on. All right? Now, the well ordering principle doesn't tell us how many such well orders can be defined on any non-empty set. In fact, here in this illustration, we provided 2 more well orders for the set Z. Okay? So yun yung well ordering principle. It guarantees that we can always define a well order for any non-empty set. Okay? So we will skip the proof, or we will not prove the well ordering principle, because the common proofs for the well ordering principle involves either Zorn's lemma or the axiom of choice, which we will discuss in the next video. But before we end this recording, let's look at some concluding remarks here. Actually, there are just 2. Theorem 15 is just the well ordering principle for the set of natural numbers. Generic yung well ordering principle na nasa theorem for theorem 13. This will work for any non-empty set. Pero pwede nating i-specify to or i-instantiate to taking A equals capital N. And this might come in handy, this version might come in handy when we go into Peano's axiom later this week. All right? So it says that every non-empty subset T of N has a first or least element. Well, you can prove this using Theorem 14, even though this is just a retranslation or a specification. Kasi si N ay non-empty. All right? So ibig sabihin, by Theorem 13, there will exist a well order in N. Kung meron kang well order kay N, kahit anong subset niya ay may first element. And that's what the conclusion of Theorem 15 is saying. Okay? And then the well ordering principle, specifically Theorem 15, allows us to extend the principle of mathematical induction for natural numbers to any well-ordered set. Kasi kung maalala nyo yung discussion natin ng PMI, meron yan 3 bahagi. Una, any proof by mathematical induction has 3 parts, namely, first, the basis step. And in the basis step, we must show that the statement is true for the first element of the set for which it is claimed. Kung ang theorem mo kiniklaim na totoo siya sa lahat ng natural numbers, ang basis step dapat ipakita natin totoo siya kay n equals 0. Or kung sabi niya, the statement is true for all n greater than or equal to, say, 7, the basis step will require you to show that the statement is true for n equals 7. Now, it only hinges on the fact that we are showing it to be true for the least element of the subset of n being used in the theorem. Now, you can forget about n and take it in a more abstract fashion na kapag ka pala meron akong well-ordered set, pag meron akong theorem about a well-ordered set, sinabi ko na property P is true for every element of this well-ordered set, then I can use the extension of the principle of mathematical induction to show that that statement, although not about the set of natural numbers, will be true for the well-ordered set. And I will do so by just replacing the basis step by showing that the statement is true for the first element of the well-ordered set. Okay? Now, but we will not go too much into that. Perhaps you will use this when you go to, say, Math 103, when you talk about, say, the extended or the strong or the weak or the extended principle of mathematical inductions for integers and so on. But for Math 101, I think that's what we will just talk about. All right? So that ends this video about the well-ordering principle. I hope you guys got something from it. Watch out for the next video. This will be about Zorn's lemma and another one about the axiom of choice. All right. Thank you guys for watching. See you on the next video. Bye.